morning. Today we'll start getting ready for probability by reviewing the counting principle, permutations, and combinations from earlier courses. So please open up your Inspire document called Counting Principle, Permutations, and Combinations, and let's go to page 1-2. So today's pretty definition heavy, not much else to do, but again, it's mostly review, so fast forward, skip around as much as you can and want to. So first example, when you toss a fair die, how can it land? Well, when you toss a die, it can land 1, 2, 3, 4, 5, or 6. Each of those results is called an outcome. But what happens when you toss a fair die and flip a fair coin? What are all the possible outcomes? So this is when you list them. So we could say maybe we get a 1 and a head or a 1 and a tail, a 2 and a head, a 2 and a tail. And you just go through and you list all the possibilities. In earlier classes, when you probably first started with probabilities, maybe in middle school, maybe even earlier, you might have made tree diagrams, and we'll still use those occasionally. So once you have your outcomes listed, you need to know that that set of all possible outcomes is called the sample space. So when you read some of these terms, you'll know what you're talking about. Page 1-3. So counting principle. The counting principle says if one activity can occur in any of m ways, and the second activity can occur in any of n ways, then both activities can occur in the order given in m times n ways. It's multiplication. So, for example, consider a set of 3 cards lying face down numbered 4, 6, and 8. Cards are drawn one at a time and not replaced, not put back in the pile. The numbers are used in the order in which they are drawn to form 3-digit numbers. So how many possible outcomes are possible? Well, there are 3 cards. So the first card, or the first time you draw a card, there are 3 possible ways. And then you don't put that back, so then there's 2 possible cards you can draw, and then you're just left with 1. So it's 3 times 2 times 1, which is 6 possible outcomes. For part B, how many outcomes are greater than 800? Well, the only way you can get a 3-digit number greater than 800 from those 3 digits is by starting with 8. So the first card you have to have, there's only one possible way, and that's the 8. And then there's only 2 cards left, so 2, and then there's only 1 card left, so 1 times 2 times 1 is 2. And how many of the outcomes are odd? Well, none of them, because there are no odd numbers, and an odd number has to end in an odd number. Page 1-4. A subset of a sample space is called an event. There are 2 kinds of events that we'll deal with, dependent and independent, and they're pretty much what they sound like. Dependent events depend on each other. When you have those replacement problems with cards, what just happened in the earlier problem, those were dependent events because getting a number greater than 800 depended on me getting an 8 first. So those are considered dependent events. Independent events don't depend on each other. Independent events are crucial in statistics courses later on, and we can only do most of our statistics if our events are independent. So 2 different definitions for you to kind of start thinking about. We're going to review permutations and combinations again today. A permutation is an arrangement of objects in a specific order. Now remember, in algebra class we talked about how when you get your locker combination, they should really call it a locker permutation, because the order at which you do the numbers on your locker, matter if you can get your locker open or not. So it really should be called a permutation lock, not a combination lock. That might help you remember. So for example, if 4 students are scheduled to give a report in class, how many ways can those students give the reports? Well, in the beginning there are 4 people to choose from, but once 1 person's gone, you're down to 3, then you're down to 2, and then you're down to 1. So 4 times 3 times 2 times 1 is 24. We could also call that a permutation. 4 people getting chosen and filling 4 positions. 4P4 would be that permutation. Now, for the second example, we have 20 students in class, but only 4 of them will be asked to give a report today. How many orders can they give the reports? Well, there's 20 people in the class to choose from to go first, and then once they've gone, there's only 19, and then 18, and then 17. So you would multiply 20 times 19 times 18 times 17 and get 116,280 possible orders. If we wanted to call this a permutation, which it is, it would be taking 20 students and putting 4 of them in order, 20p4. Now, in those two cases, there's not repetition. On page 1.6, there is, first of all, the definition of a permutation. You start with the top number, say 20 in that last example, and then keep subtracting 1 until you've gotten through that many terms. So 20p4 is 20 times 19 times 18 times 17 for 4 numbers. Permutations with repetition. So, for example, we may want to arrange the letters in the word 11. Well, one E is no different from any other E, so there's repetition. So what we do then is we get rid of all those repeats. And the way we do that is by taking the number of letters factorial and dividing by, so we're going to make this a fraction, the number of repeats factorial. And if there's more than one repeat, you multiply them. So for example, in this problem, 11, there are 6 letters. So I have 6 letters, I'll factorial that. And there are 3 E's that are repeated. So I'll divide out those 3 repeats. Now for review of factorial, those exclamation points don't mean that they're excited 6's and 3's. They mean permutations, essentially. You start at 6 and multiply down all the way to 1. And for 3 factorial, you start at 3 and multiply down to 1. And when you do that, you get 120 possible ways to arrange the letters in the word 11. Okay, so now that we're talking about repeats, let's talk about combinations. For example, I have 5 members in a club: Adam, Brian, Celia, Donna, and Elaine. They volunteered to represent a club at a competition, but the club can only send 2 members. How many different teams can they send? Well, you can start thinking about the different combinations of pairs. So maybe we start with Adam, and Adam goes with Brian, or Adam goes with Celia, or Adam goes with Donna, or Adam goes with Elaine. Now those are all the possible combinations with Adam. So now we're going to shift to Brian. Well, Brian and Adam are already a pair, so we don't repeat that pair. So maybe Brian goes with Celia, or Brian goes with Donna, or Brian goes with Elaine. We're done with the Brian possibilities, so we can go to Celia. Well, Celia is already paired with Adam here and Brian here, so Celia can only be paired with Donna or Elaine. And then you move to Donna, and Donna's already been paired with Adam here, Brian here, Celia here, so Donna and Elaine are the only pairing left. And after that, there's nobody else, because Elaine has already been paired with Donna, Celia, Brian, and Adam. So if you count these up, there's 4, 5, 6, 7, 8, 9, 10 possible ways, 10 possible teams that they can send. So what we did is we took out all that repetition. The combination is an arrangement of objects in which order does not matter. It doesn't matter if we said that Adam and Brian were a pair or Brian and Adam. It's the same darn pair. So it doesn't matter the order that you say them in. And here is an important definition of a combination. The combination of n things taken r at a time is that same permutation divided by that bottom number factorial to get rid of the repeats. It's important that you know this definition. Yes, you can use your calculator 90% of the time, but knowing this definition and seeing some patterns with combinations will save you a ton of time. And time is of the essence on the Regents exam. And that is it.